Good morning and good afternoon, depending on where you are. Thank you for giving us the opportunity of share our project with you. My name is Elyka Abello. I'm CTO of Innova Space, and today I will talk you about our low-cost satellite architecture proposal for communications in areas without mobile network coverage. So first, I will talk a little bit about the origin and evolution of the project. Then I will present the problem that we are trying to solve. Then the solution that we are proposing to solve it. And then the first satellite that we are building and we will launch soon, as Caio said. Then I will show the results of the first study of the constellation proposal, and finally conclusions and future work. So everything burned in 2019 in a public school of Mar del Plata, Argentina, when our CEO, that is a professor in that school, is Alejandro Cordero. He wanted to introduce aerospace development and new technology to his students. So he began the project that was named Arduino, as you can imagine, because it worked with Arduino and other COTS components. To show his students all this satellite technology and what can it be done with it. So the project was an educational and only like engineering model of an 1P pocket cube. It has a lot of media repercussion and in local authorities. So they won a scholarship from the local government to go to attend in Glasgow to the third poker cube workshop and present their project. The guys also present their project in the second International Academy of Astronautics Latin American Symposium in Buenos Aires in the same year. So during this whole like workshops and Congress and when they were working with this, they realized that the pocket tube could be used for more than only training and educational purpose. So they came up with the idea to use pocket tubes to give a solution to lack of coverage of mobile communications for IoT devices. The idea began and the startup began in 2019. And it became a business model. We began to participate in a lot of contests for a startup to validate the idea and the business model. And we got to the final of 5 of this contest in 2020 and 1 more in 2021. And we won 2 of them. One was the biggest, that is Naves, and the other one was Mar del Valle in this year. In the meantime, we also get some funding, first from an accelerator called Neutron. It is a local accelerator from Mar del Plata, and also from Argentinian government, which give us more than $166,000. This is what is funding our first satellite. We also have a technical milestone in June this year that will launch a model of our satellite in a rocket that is also built by an Argentinian company called Tlon. It was a suborbital flight, but we could test all the communication and telemetry system for the satellite. And it was like very cool because it was an Argentinian satellite launching in an Argentinian rocket. And our next milestone will be the launch in Alba's next pod, that it should be between December and January. So it's very soon. We are running with that. So what's the problem that we are trying to solve here? As some of you might know, 80% of the world is without coverage of any kind of communication. And Latin America is not the exception. 70% of Argentinian land is without any kind of coverage. And this is not going to change soon because according to the ITU, between 2017 and 2019, the mobile phone coverage increased only by 1.3%. And this is because it's not profitable for companies. As you can see in this graphic, To deploy all the facilities to give communication and mobile network to remote areas, it costs 35% more than doing in urban areas. And it also, you have less customers in remote areas. So it's just not profitable for them with the current technology. And the real problem here is that agriculture is made in these remote areas that have no coverage. And according to the FAO, we need to raise the production in 70% by 2050 in order to give food to all the population in the world. And the land is not going to grow. So we need to make the same land with more efficient technology, So we need to bring communication so they can use modern technology like IoT to increase the production. So our solution will be to provide a plug-and-play board for satellite communications with a low-cost constellation. It will connect the sensor in the field with our satellites, and then the satellite will send the data to a ground station, and then the data will go to a cloud, and the user can reach from the cloud everywhere. Here you can see the diagram for the system. So you will have a gateway, so you can collect like several sensors in one gateway. This gateway will be connected to our boards. The board will be connected to the satellite, and then the satellite will download the data to a ground station. Then it will go to the cloud, and the customer can get it. So how I will plan to make it this low cost compared with other companies that already provide this service? We are planning to use Picosatellites. Particularly, the first one is it will be a pocket cube. I think we are all familiar with the pocket cube concept here, so I will go further. So the advantage comparing with the traditional geostationary satellites for communication are a lot. Other than the obviously advantage that is smaller and lighter, and then it's cheaper, and also the launching is cheaper. We have the development cycle that is it could be less than 1 year for pocket cubes, compared with a traditional satellite that it take at least 5 years. So this can make that you can upgrade your technology faster. There is also the thing that our satellite will be in low Earth orbit. So the ground station and user terminal can be smaller and cheaper than for a geostationary satellite. We also have less vulnerability to the line of sight to be blocked, because instead of having one steady satellite, we will have a lot of satellites that will pass by different sites. So the user terminal can connect to one of the satellites at one point. So this is the architecture of our first satellite. It will be a demonstration satellite, so it won't have any commercial purpose yet. But we will learn a lot. We have learned a lot in the whole process, and we will learn a lot of the results that we will get there. So it has the normal subsystems and a structure subsystem, communication subsystem that is unified. So for this satellite, we will be using just one communication system for both the payload, that is the user data, and the housekeeping data. We have the electrical power system. We have the onboard data handling system, and an attitude determination and control system. And we also have a second payload that is for experimental use. We have experimental magnetometers that a partner company developed for us, and he wanted to test it. So we will put it on orbit. So you can see the red lines are the power lines, and the dashed line are the data lines. This is the structure. You can see it's a 2P pocket cube, and it has deployable solar panels and a deployable antenna. So the structure is made from 2 aluminum frames assembled with treated rod. It has a second system of treated rod to fix the internal electronic boards, and the external electronic boards are screwed to the frames. And it also have like I mentioned before, 2 deployable solar panels and 1 deployable antenna. The mechanism for deploy these elements is just measuring tape. It has been used for several Pocket Cube and CubeSat missions, so we're going with the simple way. As for the inside and the electronic systems, we have the power control unit, that it has a maximum power point tracking architecture. It has a battery management system, and it has 3 regulated buses. 2 are 3.3, 1 for critical load and 1 for non-critical loads, and also 1 4.2 volts regulated bus. It has 2 lithium-ion batteries, and it has 5 solar panels. 2 are deployable and 3 are body mounted. We use a space grade solar cell of high efficiency, 30% efficiency with a lot of heritage solar cells. As for the communication system, we will be using UHF band for a maximum of 1 watt of transmission power, and we will use a monopole antenna. For the attitude determination and control system, we will use active magnetic stabilization. So we will only stabilize the satellite. We won't actually control the attitude, and we cannot have some appointment. And also we don't need it because the antenna is almost omnidirectional. We have some sensors to achieve this. These are 3-axis accelerometer and 3-axis gyroscope. And we also have a GPS. And we have, as actuator, we have a 3-axis magnetorquer. For the OBDH, we are using a microchip at some D51, and flash memory, SRAM memory, and SD memory to storage the whole data until it can download it in the ground station. For the thermal control system, we are using just passive thermal control. So all the boards are painted in white, except for the one that is closest to the batteries, that is black, to maintain the heat during the eclipse period. And we perform the analysis, and all the components should be working within their operational limits. As for the constellation, we have performed the preliminary analysis for a LEO constellation. We use a sun-synchronous orbit, and we got that we will need between 50 and 150 satellites, depending on the maximum age of data that we desire. Now, the advantage, the characteristic of the IoT applications that we want to cover is that we don't need real-time data. So we can have like 5 minutes or 10 minutes of age of data, because we will only be censoring like temperature or something in the fields, and it doesn't have like a very high requirement with this time. So the minimum number that we think we should have is 80 satellites for an age of around 10 to 30 minutes each data. Actually, we're aiming to 100 to reduce this time to less than 5 minutes. And the latency with this 80 satellite will be less than 5 minutes. So as a conclusion, here we propose the high-level proposal of the constellation of picosatellites to provide low-cost communications for IoT devices. We also show the design of the first demonstrative low-cost satellite that will be complying with the Pocket Cube standard, specifically a 2P. We also performed the first analysis and simulations of coverage for a LEO constellation. As you can imagine, we have a lot of work to do. First, we need to develop and implement a double radio frequency systems. As I told you, right now we are using same communication system for housekeeping and for user data. But for the commercial use of the constellation, we will have a lot of user data. So we need to change the download system of this data. We also need to develop our own protocol to allow massive interconnection of dispositive with the light tolerant networks. And we also need to evaluate the feasibility of incorporate propulsion system to allow orbit correction and deorbiting. I think this is really important because first we will have a longer life of the satellites, and second we can deorbit it quick, so we won't contribute to the debris problem that we have right now in the space. And finally, we have to continue the development of the user's terminal and the ground station. For this will be very helpful the satellite that we are going to launch soon to develop the user terminals. So that's all for today. Thank you very much for your attendance. And if you have any question, please, well, you can do some now, but if there is no time, you can send it through the email that you have there or social network. Thank you.